This information is brought to you by Charles Sturt University.
Hi, this is a short video giving a demonstration of how to do a change of variable in a multiple integral. This one's slightly different to some previous examples from tutorial 6, where I'll define the transformation in terms of u and v is equal to a function of x and y, rather than the other way around, rather than x, y as a function of u and v. So it's the transformation of the other way around. So what we've got is we've got a parallelogram. So I've got a picture over here. So I've got a parallelogram. So it's a parallelogram, which is got some vertices. So so 4 different vertices, and given vertices, you can work out the equation for the line. So as marked the diagram, I've got the lines which bound this parallelogram on my diagram. So what I want to do is I want to integrate over this parallelogram, so this particular function, so 3x minus y. So what I want to do is I want to go, well, if I try to do it directly, right, I have to treat it as a type 1 or type 2 region, which it isn't. So you could get a better colour might be good. So you could split up into 3 different regions, and each of these 1, 2, 3 regions would then all be type. It would all them be type 1 regions, and then you can integrate over each of them separately. So split the integral up in 3 parts and add it all up. That's going to be a bit time-consuming. So another approach is try to transform the variables. So change the variables so that it's easier to integrate. I have a nicer region. So just observing, notice that the bounding lines, one line up here is x plus 2y equals 9, the other one is x plus 2y equals 2, and so I notice that this x plus 2y is mentioned twice, and so maybe just letting u equal that would make nice bounds. So u equals 9, u equals 2 then, so they're pretty good bounds. And the other two lines are 3x minus y and 3x minus y. So how we let v equals 3x minus y, that's just really by observing that the parallel lines have this consistent form, and so we can easily do it. So this is a different type of transformation to some of the previous examples, so I hinted at it before. So in a question and assessment item, I would tell you what these are, but just show you where they sort of come from. So what I want to do is I'm going to try to work this integral out. So I've got to change of variables, so I've got to work out how they all flow through. So what we often do is, in order to deal with things, we often would work out uv in terms of x and y's, like it is here, and the other way around, so x, y's in terms of u's and v's. And sometimes that's helpful to do things like subbing in, working out Jacobian, etc. You can actually work at everything, in this case at least, by just using u's and v's. So that's what I'll try to tackle, but there is alternatives. So I guess the first thing I want to do is find the Jacobian. So the Jacobian normally is a absolute value of a determinant of matrix with lots of partial derivatives in it, and we normally write it down as the partial derivatives of x and y with respect to u and v, and then take the derivative. So something like this notation. But we don't know x and y is a function of u and v, so a little trick is that the reciprocal, or the Jacobian, is actually the partial derivatives of u's and v's with respect to x and y's, and then do our normal stuff, I take the determinant, absolute value. So this is a nice little trick, and we can do it in this case. So that would be the absolute value of the determinant of a matrix of partial derivatives. So it would be partial derivative u with respect to x, u with respect to y, v with respect to x. v respect to y. And this is easy doable because I've got functions for u and v at the top here. So u up at the top, if I take partial with respect to x, I just get 1, partial with respect to y, I get 2, partial derivative of v with respect to x gives you 3, partial derivative of v with respect to y gives you -1. And since it's linear, it just ends up being different coefficients because it's a linear function. So I'm going to take the determinant of that matrix and then take the absolute value of what's resulted. So taking the determinant, I'm getting 1 times -1, which is -1, -2 times 3, so -6. So I'm getting -7, that's my determinant. And then taking the absolute value of that, and so which just gives me 7. So a mistake that some people might make is they forget to rid of the minus sign, and so you'll got a sign error in the end. So it's really important to make it positive. So I'll speak more of that in a second. So our Jacobian is 1/7. Now, this is change of variables is really just a generalization of the idea of substitution for one variable. With substitution, we never actually take absolute values anywhere. Like that's not a concept we see in one variable. So why do we have to do it here? Well, when the answer is with one variable, if we change things, if the Jacobian, which ends up being the derivative, happens to be negative, then what we do is when you do it, the limits end up being in the wrong order. So you go from, instead of the lowest to highest, like you would normally, go from the highest to the lowest. And so if you flip it around, so if you put them in the right order, it introduces a minus sign. That minus sign makes an absolute value. That's sort of where it works. So with one variable, we can account for the minus sign just by how we do the limits, and it's all okay. When it comes to two variables, like here, the limits are immensely more complicated. And instead of trying to have to worry about, oh no, maybe we've flipped it somewhere around the way, it's much easier to just do the limits from the region just as it looks. And in order to worry about orientation, we worry about the orientation by taking the absolute value of the Jacobian just to make it all right as rain. So that's the difference. So we're dealing with the change of orientation, which is what it is here, by the Jacobian rather than the limits. Just because it's a bit too hard. I mean, it's doable. It's doable, but it's quite a bit of serious bookkeeping you have to handle, and it's often easiest to do it here. So how about I'll show you what the resulting the map region is, just to try to explain the change of limits in a second. But anyway, so we've got the Jacobian, and so our differential, so before our differential was, say, dA, or say dx dy. So the new, when we change it, it'd be the Jacobian times by du's and v's. Let's make it dv du, du dv, doesn't really matter, I guess, at this point in time. You'll make the choice later on, really. And so the new differential is going to be 1/7, say, dv du. So use the Jacobian to change the differential. We also need to change the integrand. So the integrand before, just looking at it, was 3x minus y. That's the integrand we need to change. Now, what we could do, normally, what you have to do is you get the value functions for x and y in terms of u's and v's, sub it in, and it gives you a new u's and v's expression. But in this case, you go, hold on a sec. I let v equals 3x minus y. So 3x minus y is just equal to v. And so I don't actually have to do the inverse transformation directly. I can just go, oh, hold on a sec, I know what that is already, and fantastic, done. Makes it easy. So you have to look at the new region of integration, is the next one. So change the differential, change the integrand, next we change the limits, essentially, but region of integration. So the old region of integration was this parallelogram. And instead of focusing on the points, we can just focus on the side. So this side here, the x plus 2y is equal to u, so it's u equals 2. This one becomes u equals 9. The 3x minus y is just v, so this becomes v equals 6. And this one here becomes v equals -1. So you can see that by just applying this transformation just to the bounding lines, then we quickly get what the new bounding lines are for new stuff. And they're nice. These are just either vertical lines or horizontal lines, depending how you define it. So here's region a bit too big. Let's make it smaller. This is the new region. So it ends up being just a nice rectangle. So as I said before, we've got u equals 2, u equals 9, v equals -1, and v equals 6. So, and the reason I've done is just, just for an example. So the 3x minus y equals -1, that's one of the bounding lines. I've just sent that to being v equals -1. I've done that to all 4 lines. So I can see the new region is then, used between, say, 2 and 9, and v is between -1 and 6. And since it's a rectangular region, heaps easier to integrate, much easier. So just some little points about these things. So what I've done here is just label the vertices. So I've got circle, it's supposed to be diamond, asterisk, square. So if I label the matching vertices here, so that'd be the circle. The diamond, instead of being down the bottom right, it actually goes up. Asterisk is still the opposite one, and we get the square. So previously, it was sort of going around the vertices as I labelled them was sort of anti-clockwise. Now the labels go around clockwise. So what we've done is we've actually changed the orientation. So the transformation changed the orientation. So when you do that, if you didn't adjust the Jacobian by taking absolute value up here, then you actually have to do the limits in different order to match the orientation. Which is tricky because you have to be careful about orientation, and that's why it's just easy to take absolute value at the top here. Then you can forget about it, which is normally much easier to do. But anyway, now we've got those things set up. I was just trying to start explaining things, by the way. So now we've got everything set up. Now we can just do the integral. So our previous integral was integrating over our parallelogram of 3x minus y dA. So now we can integrate. So the region integration is no longer the parallelogram, but it's the rectangle. And so it's going to be, you can make it d v to u. So the limits for u are 2 to 9, and the limits for v are -1 to 6. So that's my new limits. So just change the parallelogram, complicated to rectangle, easier. The 3x minus y is in old integrand, that's changing to v. That's what I've got at the top here. And the differential, dA becomes the Jacobian, 1/7 times by the new du to v, or v to u. And that's equal to 1/7 integral from 2 to 9, integral -1 to 6 of v to v to u. And because it's rectangular, not a very complicated expression here, you could do it by direct integration in a fairly straightforward fashion, which I encourage you to do. And that's perfectly fine to do. Just want to show a different trick for it though. Let's just look at this integral here. So this is essentially an integral of v dA. That's pretty much what it corresponds to. So this looks remarkably similar to our formulas we know for centre of mass. So this expression here, well, to work at centre of mass, this is going to be related to, say, centre of mass, and it's going to be, say, the v coordinate. So this is going to be related to the c coordinate of mass. So normally what you do is you have to divide this integral by the area, or which is the total area. And so pretty much the double integral of v dA is end up being the area times by the corresponding v coordinate centre of mass. That's true in general. So you've got double integral of just a single letter times dA, then it's going to be the total area or total mass in general of that letter, coordinate of the centre of mass. Now, which is only good if there's a nice shape. But in this case, the shape's a rectangle. So back to our rectangle, And so the center of mass is going to be pretty much right bang in the middle of it, right? So the center of mass for a rectangle, quite believably, is right bang in the middle of it. And we just know the v coordinate. So v goes everywhere from -1 up to 6, and so we'll take the average value really. So that average value, add them up. So 6 minus 1 gives you 5, divided by 2. So the v coordinate here will be 5 on 2. And you can work at the u coordinate the same way, just average of 2 and 9. 2 plus 9 is 11, so it gives you 11 on 2. Would be the u coordinate at the center of mass. And so what I can say in this case then, that my original integral is equal to the 1/7 from before, times by the area. Well, it's a rectangle, so areas of rectangles is pretty easy. So it's 9 minus 2 gives you a length of 7 in this direction. And 6 minus 1 gives you 7 this way. So it's actually a square, as a matter of fact, even. So the area would therefore be 49. That's the area. And then multiply this by the v coordinate of the center of mass. And then just do the product. So 1/7 of 49 gives you 7, times that gives you 35 on 2, which is the answer. And again, you could have perfectly done it just acceptably by just doing the integration directly. But it's useful just to see some other alternative methods that you can apply. So that's the end of the question, and that's the answer. So you've worked out the integral. But just reiterating, when you try and do an integration by using transformation, we need to work out the Jacobian. You can do it directly or indirectly. And it's good just to remember that as an alternative choice. You could have done this one directly. If you did it directly, then you'd have to have inverted this, and since it's a linear, I would just use matrices and use the inverse matrix to work out the inverse transformation. And then you could have just plugged in the formula, normal formulas directly, etc. And if you were to, and you could have used the point. If you're using the points rather than the bounding lines, the inverse transformation is certainly a preferred option. But just giving you other options of how to do these different calculations. So I hope that helps. If you've got any more questions about this particular question, please ask on the discussion boards. Thanks.